Hello and welcome to Aerospace and Mechanical Lab 1. This is going to be the last lecture that I will upload. This is the lecture about fluid flow in pipes, the Lab 10. Today we are going to review fluid mechanics. We are going to talk about what is a fluid and move on to the different categories and classifications of fluid. And eventually we'll talk about Lab 10. You have to keep in mind that Lab 10 you're going to see in the lab, the actual guide, will be a little different from the pictures we have here. I haven't had the time to update the pictures yet. The changes are pretty new. But I don't think you're not going to have any issues doing the lab using this lecture. Okay. The first thing we want to be able to define is what is a fluid. A fluid is defined as a substance in the liquid or gas phase. What is the difference between a fluid and a gas? The main difference is a solid, or between a fluid and a solid. The main difference is a solid can resist a shear stress. It deforms a little bit. During the elastic deformation, when you remove the stress, the solid will go back to its original location. Fluids, though, cannot resist the shear stress. What does it mean? It means that if you apply shear, it will keep deforming. Deformation won't stop. It will keep deforming, which essentially means that it will keep moving. The layers of fluid are going to keep moving on top of each other. Which essentially means mathematically, in solids, a stress is proportional to a strain. Shear stress is proportional to angular strain. And in fluids, a stress, that is shear stress again, is proportional to a strain rate, which we usually see as the gradient of velocity with respect to y. When you apply a constant shear, a solid will stop moving and the fluid will never stop moving. I will essentially approach a constant rate of strain. And a constant rate of strain here essentially just means a constant velocity. A fluid will deform like this. So essentially, this is a rubber. When you put a rubber in between two plates, one of them is fixed, the other one is moving, there will be shear transformed to the rubber from this side. So this is how a solid moves. There's a strain, but the fluid is this deformation will keep happening and happening and happening. This will never stop. Fluid mechanics, so is the science that deals with the behavior of fluids. This behavior can be behavior of fluids at rest, like the hydrostatic pressure analysis, all of the, I'm sure you have had a lot of fun in your fluid mechanics course with this, or you will if you haven't taken fluid mechanics yet. Or the other area that fluid mechanics focus on is fluid dynamics. Essentially, fluid dynamics talks about the interactions of fluid particles with each other and solids and their movement. Fluid mechanics itself is divided into different categories of study. One is hydrodynamics, which talks about the movement of water. One is gas dynamics, which talks about the movement of gas. So the topic of the winter lab was gas dynamics, actually. A subcategory of gas dynamics is aerodynamics, which was the exact topic of a winter lab. And then there are other categories of fluid mechanics, meteorology, oceanography, and hydrology, that are not of our interest. Today we are focused on hydrodynamics, essentially the relation between velocity of the movement of fluid, water here specifically, in pipes, the relationship between that velocity and the pressure differential, and all of the losses due to viscosity and whatnot. Okay. We can define the movement of fluids itself, not the science of studying fluid. We can divide the movement of fluids itself into different categories. One category talks about the viscosity of fluid, whether viscosity is important or not, the first one, which essentially means that we can have viscous flow where viscosity is dominant and important, versus inviscid flow where viscosity is non-important. The next field of categorization is flow inside pipes or over surfaces, internal versus external flow. So our internal lab was a case of internal flow, whereas the fluids lab, external flow, I'm sorry, whereas the fluids lab is a case of internal flow, movement of flow inside pipes. And the other category is related to density, whether the density changes with respect to pressure or not. If the density changes with respect to pressure or temperature, we call that flow compressible. You can think of movement of gases in general at higher speeds. It's very compressible. But we can safely assume that movement of water inside pipes is very incompressible, meaning that the density can be assumed constant throughout the flow. And eventually the other categorization of the flow, laminar versus, I guess this is not the last one yet, but this is the most common one, laminar versus turbulent flow, which talks about the velocity and Reynolds number of the flow. Laminar flows are orderly, turbulent flows are chaotic. They have a lot of mixing, they have a lot of eddies, vortices, and whatnot. Turbulent flows usually enhance heat transfer and energy removal. At the same time, they create a lot of drag or pressure drop that does not exist in laminar flow. So laminar flow versus turbulent flow in pipes do exist, but I'm not going to ask you to tell me whether the flow is laminar or turbulent in this specific lab. And two other types of flows are natural versus forced flow. This is mainly a topic of heat transfer. Wherever you have heating happening without an external flow outside, you will have natural convection or natural flow. The air is going to start moving because of density difference instead of any pressure from outside, like a fan or something similar to a fan. And then eventually we have the steady versus unsteady flow. Steady flows do not change with respect to time. Unsteady flows do change with respect to time. So at each point, the velocity of one particle at one point in a steady flow is constant. The velocity of one particle at one specific point can be not constant for the unsteady flow. Can be constant for the steady flow, can be variable for unsteady flow. So again, our focus here is pipe flow. Pipe flows are viscous, meaning that the effects of viscosity is important, and this will show up in the losses, the discharge coefficient that we are going to calculate later on. The flow is internal, which essentially means that it is moving inside pipes. It is incompressible because we are dealing with water. It is steady because we let the system stabilize. We just let it run for a couple of seconds and then make the measurements. And it is forced. I'm sorry, it says natural, but it should say forced. Meaning that there is a source that is source for pressure difference because we have a pump in place that is pumping water. This is how the lab looks like. It used to look like, at least. So I have made some modifications. This paddle flow meter is removed and replaced by a digital flow meter. You're going to see in the lab. And we don't really make pressure measurements over the valve. So what happens is there's a reservoir that is connected to a pump directly. We have one pressure probe here and one pressure probe after the pump to measure the pump pressure differential, essentially the pressure difference that the pump is causing. And then that is sent to a flow meter, a digital flow meter you're going to see in the lab. That flow meter directs the flow to a mechanical valve, and then there's a venturi on which we make two other pressure measurements to calculate the pressure differential of a venturi. The diameter, this is how a venturi looks like. Essentially, a venturi is a converging, diverging nozzle You can see there is convergence here, meaning that the area is decreasing, and there is divergence. In the middle, we have the necking. Essentially, we have the throttle of the valve. The diameter ratio, this diameter divided by this, is a very important factor when it comes to the flow and pressure differential of a venturi. Okay, so you have to know the diameter ratio of the venturi you are using, and we have different diameter ratios in the lab. The diameter ratio is usually written on the side of the venturi, so you can just take it from there. But if it wasn't written, you can use the parameters we have here. So you can use these two diameters for your diameter ratio if you need them in your calculation. Okay, so essentially we are measuring the flow rate with the venturi. Venturi measures the pressure differential, but the software we are using convert this to flow rate using the Bernoulli's equation essentially. And then we use the digital flow meter to measure the flow rate here. We also have a power measurement to calculate the power input, the power usage of the pump. And we also have using this watt meter right here. It looks different in the lab. We have updated the watt meter. And all of these are given to a computer. So your job is to measure the pressure ratio, pressure difference before and after the pump, measure the flow rate, either manually, meaning that you will be given pictures, and using those pictures you can actually measure the volume of the fluid divided by the time, record the time to calculate the manual flow rate. That also works fine. And we have a pressure probe installed on the venturi itself to measure the flow rate, the ideal flow rate of a venturi. This mechanical valves will let you essentially close and open the valve to change the flow rate. And you have to do this 3 to 5 times to have different measurements at different flow rates. Then, how do we calculate the flow rate of a venturi using the pressure differential? This is your equation. This equation can be calculated, can be derived using the conservation of mass and momentum equation, which essentially means that Bernoulli's equation for this specific scenario. I'm sure you are familiar with all of the parameters here. We have the area, we have the velocity, outlet velocity, we have the area ratio, which is essentially the diameter ratio. This is where the diameter ratio comes into play for you. We have the gravitational acceleration in the British units. If you are using SI units, you don't really need to use UofSC. And we have the pressure differential that is measured by the venturi. So in the lab, again, we either calculate the flow rate for you ourselves automatically using the software, or we might ask you to do the pressure differential and put it in this equation to calculate the flow rate. But the idea is that this flow rate is calculated using the Bernoulli equation that is built on a lot of assumptions that do not necessarily exist here. The main assumption is neglection of viscosity. We cannot and we should not neglect the viscosity in water flow inside the pipes, which essentially means that this flow rate is an ideal flow rate, it's not the real flow rate. So what we do is we measure this ideal flow rate and then we divide it by the actual one, which is calculated, which is like it's measured using the flow meter we have installed or using the manual flow meter, and then just divide the two by each other to calculate a discharge coefficient. This discharge coefficient tells you how much you deviate from the ideal scenarios. Essentially, it tells you how important the viscosity is in your calculation. And we can have graphs, as you can see, as you increase the Reynolds number, essentially means that for our case is as you increase the velocity, there should be an increase in your discharge coefficient, but at some point it will plateau and the discharge coefficient would not change anymore, meaning that the effects of viscosity increases as you increase the flow rate. but plateaus at some point. The other thing we want to do, I'm sorry, it says lab 7 here, this is lab 10. Again, the other thing we want to do in this lab is to analyze the fluid flow in pipes, essentially to calculate the efficiency of the pump that is pumping our water. You have this pump installed. We are measuring the pump power using the watt meters. We are measuring the pressure difference, and we have measured the flow rate. Using these parameters, you can calculate the efficiency, and you have to essentially do the other calculations you are doing. This lab is this efficiency calculation. And these are the questions you need to answer. Please follow the lab instructions because I have updated the lab instruction a little bit. And we expect to see these graphs. We don't have the valve pressure differential measurements anymore, so you don't worry about the valve. And we only care about the pump pressure differential and the venturi pressure differential and the flow rate. That's it for today's lecture. Please let me know if you have a question, and enjoy the last lab.